Welcome back, everyone, to our conversation on redox reactions and specifically oxidation numbers, which is just a fancy word to say charge. Why are we talking about oxidation numbers or charges now? Well, we're talking about those because, as you hopefully recognized from the previous video, when we talked about oxidation reduction reactions, we used the charge or the oxidation number of a species to easily determine if something was being oxidized or reduced. In the previous example and in the previous video, the charge of both the zinc and the copper were clearly shown in the problem, and so you could in that example easily determine if something is being oxidized and what's being reduced. And similarly, what the oxidizing agent and reducing agent are. But if life was only so straightforward or easy, many times you will have a chemical equation, kind of something similar to what's written here. You will have a chemical equation and asked to determine what's being oxidized, what's being reduced, what is the oxidizing agent, and what is the reducing agent. And so looking at this equation, hopefully you recognize two things. First, that this is a combination reaction, right? I have two simpler substances giving me something more complex. So this oxidation reduction reaction can also be classified as a combination reaction. But what you also hopefully realize is that, oh man, there's no charges written by any of these species. No oxidation numbers, no charges. So it's really difficult to determine what's being oxidized, what's being reduced. So to determine in a chemical equation, if you are not given charges, you need to fall back on some rules, some oxidation number rules to use to identify, to assign oxidation numbers to species in a chemical equation. And these rules, yes, you will have to memorize, but thankfully many of them are similar to monoatomic ion charges that we learned in Unit 1. So let's talk about those rules and use those in conjunction when thinking about this particular combination reaction with regards to oxidation and reduction. We're going to talk about those rules, and in this next video, we'll do some more practice problems. So the rules for oxidation numbers. First rule, each atom in a pure element, meaning an element by itself, has a charge or an oxidation number of 0, great big fat 0. So for example, if I just have solid iron all by itself, not bound to a nonmetal or in an ionic compound, the charge on that iron, when it's all by itself, is a great big fat goose egg, big fat 0. Similar with oxygen. Oxygen and O2. Oxygen all by itself, not bound up in an ionic compound. It has an oxidation number of 0 as well. So in this, let me go back, in this reaction, the O2 has a charge, let me get my little, has an oxidation number or charge of 0. What else has a charge of 0 is this calcium. It's calcium, it is all by itself, not in an ionic compound, so it has a charge of 0 as well. Now when they get bound in an ionic compound, we'll talk about that shortly. But any element by itself, charge of 0. That's the first rule. Second rule, if you have a monoatomic ion in an ionic compound, then its charge or its oxidation number is equal to the ion charge. So for example, if I had NaCl and I asked for the if I asked for the oxidation number or charge of that Cl, well, that Cl is bound in an ionic compound, so that charge, that oxidation number, is equal to the charge of the group 7 elements, the halogens, which is -1. Similar rule for the cations and the metals when they're in an ionic compound. So remembering that, let's go back to our calcium and oxygen example. So we know the charge of calcium and oxygen as a reactant, the way that it's written here. They're all by themselves, so they have an oxidation number or a charge of 0. On my product side, the calcium and oxygen, they're bound together in an ionic compound. Calcium, monoatomic ion in group 2, so it is a +2 charge. Oxygen's in group 6. It has a -2 charge. We learned about in the first unit. Okay. So that is the second rule, is that any monoatomic ion has an oxidation number that's equal to the ion charge when that species is in an ionic compound. Now, when we get to halogens bound with other halogens, things get a little more interesting. Okay. As we talked about before in Unit 1, that halogens have an oxidation number or charge of -1. However, if halogens are combined with another oxygen or fluorine, then the oxidation number of chlorine, bromine, and iodine is not 1. It's not 1, and then you use your rules for knowing that the overall charge of a molecule is 0 to determine the oxidation number of that species. What does all that mean? Let's say I have CF4. Well, I asked about the oxidation numbers. Well, fluorine, I know fluorine is a halogen. That fluorine is not combined with oxygen or another fluorine. So each fluorine in CF4 is going to have an oxidation number of -1 because it's a halogen in group 7. Now, if I have, in the second example, if I have fluorine attached to chlorine, now I've got fluorine attached to another halogen, chlorine, and I remember the rule that if halogens are combined with fluorine or oxygen, that the oxidation number of chlorine is not -1, then I have to remember that rule, and remembering that fluorine is a -1, and there's 3 of them, that means the oxidation charge of F3 is a -3. Therefore, the oxidation number of chlorine in ClF3 must be a +3, because remember, we want the sum of the charges to always equal 0. Similar thought process with ClO negative, but in this case, for this polyatomic anion, this negative sign means that the overall ion has a -1 charge. That means the oxidation number of chlorine plus the oxidation number of oxygen equals -1. So that means that my oxygen must be a -2 and my chlorine has to be a +1. Why is chlorine not -1? Well, it's not -1 because that chlorine is bound to an oxygen. So I know that's maybe sounds a little confusing. I think a better way to say this exception is that fluorine forever and ever always has a -1 oxidation number or a -1 charge. Okay? Remembering that, and remembering that the sum of the oxidation numbers for a molecule is equal to the charge associated with that molecule will serve you well with these problems. 2 more rules, and then this video will stop, and then we'll do some more practice problems. Along with fluorine always and forever being -1, oxygen is always going to be -2, except, just one exception, except with hydrogen peroxide, H2O2. In that molecule, each oxygen has a -1 charge. Thankfully, there's only one exception. Fluorine, always -1, no exceptions. Oxygen, always -2, one exception, hydrogen peroxide. Yep. And then the final two slides. When you have hydrogen with a nonmetal, hydrogen is always +1. You knew that already because hydrogen's in group 1. But with metals, hydrogen is always a -1. So for example, in NH3, I have hydrogen with a nonmetal, so hydrogen's a +1. In both of these examples, NaH and LiH, hydrogen is with a metal. So in those two molecules, the charge or the oxidation number of hydrogen is -1. And then last but not least, always remember that the sum of the oxidation numbers for all atoms in a molecule equals 0. If you have an ion, a charged species like a polyatomic ion, the sum of the oxidation numbers for all the atoms equals the overall charge of that ion. So for example, if we were to do NaHCO3 and I wanted to determine the oxidation numbers charges for each atom, I look at this and I see, well, I see sodium in monoatomic ion, so that's got to be a +1. Hydrogen's a +1. Oxygen, always and forever, is a -2, unless it's with hydrogen peroxide. There's 3 of them, so that the part of that molecule is a -6. So if I have a +1, a +1, and a -6, the only way that I can get the charges of all my atoms to equal 0 is for that one carbon to be a +4. So that's the end of the rules for determining oxidation numbers. In the next video, we're going to do many more practice problems on how to determine oxidation numbers for each atom in a molecule.